Okay, so in this video, I'm going to quickly discuss cross product and its properties, since this information is posted on your Google Drive and you can read it, and there's information in textbooks you can read as well. Cross product, to be just blunt and to the point, is a way of determining a vector quantity that is perpendicular. Now, this vector quantity can be a force, it can be lots of different aspects, and there's different other interesting applications to this technique. But it is a vector result from taking a cross product. And one of the examples is something like turning a bolt using a wrench. So oftentimes you may see different videos where people will use very long bars to turn a bolt or turn something, especially when you're changing tires. The longer that is, the better it is. And this is one of the calculations that helps get through that in terms of explaining how this works. So we'll just take a very, very brief look at it, and then we'll get into the formula or cross product. So essentially the calculation involves how much force is going to be exerted on this bolt and whether the bolt is going to be going inward into the material or coming outward. So you can either tighten the bolt by making it go in to a piece of wood or the tire rim, or it can come out. So just think of it as a screw as well. So same sort of idea. So the amount of force is the calculation, which is referred to as a moment of force, or often referred to as a torque. The calculation is based on the positioning of two vectors, tail to tail, much like dot product. Okay, and so one would be acting to turn the wrench, and the other one is the force along the actual instrument itself. And the calculation here is based on the magnitude of the force being applied in the certain direction or the rotation, along with the sine of the angle between the forces there. Okay, so there's a derivation in textbooks. You can see other videos, and I'm just going to kind of quickly go through this. So the distance between the center of the bolt and the point where the force is applied is important. So that's what your R is. So assuming the force grabbing onto the wrench here would make a difference in the quantity of force as opposed to grabbing the wrench there. Okay, so that's the difference in the calculations. The magnitude of the force directed perpendicular to the wrench. So again, what's basically going to happen is this bolt is either going to go into the material or come out. So the net force that's created in here is the magnitude of it is directed perpendicular to the wrench. So again, that's why either the bolt is either going to be going in an inward direction or an outward direction. Okay, so here's the calculation for the moment of force. And another way of looking at this or naming this is referred to as torque. So that might be a little bit more familiar term than moment of force, but it is a magnitude calculation. We'll get to the actual vector cross product calculation in just a moment, but tau is the Greek letter that's used to denote torque. And as you can see, it is the same calculation as what you have up here for the moment of force. Okay, so that gives you the magnitude. We'll get into the cross product in terms of a vector. Now, because the cross product is a vector quantity, then we need to incorporate not just a magnitude, which is this portion of the cross product, but we need to incorporate perpendicular to both of those vectors. Okay, so both of the vectors. So just to go back real quick. So this vector R and vector F, okay, so they're on a two-dimensional plane, and the other vector would be either coming out or in to the page. I don't have a three-dimensional viewer to show you, but that's where it's going to be perpendicular. So either at this point coming out right towards you from the screen, or going into the screen would be another way of looking at it. So to denote that, we need a vector quantity, and that's what this is for. Now, it is typically representative of a normal vector. That's what the N is for. The little hat symbol generally is for unit vectors. It doesn't necessarily have to be a unit vector, but it is a little bit more convenient to make it a unit vector because you're not going to change the scalar quantity at all. All right, so n is the unit vector directed perpendicular to both u and v. Better example, visually speaking, down here. Now, two-dimensionally, you might see diagrams like this one here, which again is not the greatest three-dimensional object. So again, if you're looking at the cross product between u and v, you get that n vector. Now, the order of the cross product does matter. Okay, so there is something called the right-hand rule. That's what this right hand is all about. So the way that you determine whether the vector is going in either an upward direction, like in this case, follows the thumb, or a downward direction, is based on the order of the algebraic notation u cross v. So again, if you follow the directions here, curve the fingers in the direction sweeping through u to v. So because it's u cross v, you put your fingers along here, and then curl them towards the other vector, and the direction of your thumb is going to decide which direction n is going to travel. So if you're doing it the opposite, if it was v cross u, then you'd have your palm here, and your thumb would be pointing in the opposite direction. Crossing your fingers or curling your fingers this way would have your thumb pointing in the downward direction. Okay, so it's known as the right-hand rule. Okay. Now, if u and v are collinear, so collinear again meaning they can be translated and placed on a single line, then the angle between them is 0, right? So then the cross product produces 0. In other words, the bolt will neither go into the material or come out of the material. So the net force is basically 0, and the vector would be a 0 vector. Okay, so that's something that's important to note. So any vector perpendicular to both u and v is a scalar multiple of that cross product. That's what that's indicating there. Okay, so just to take a look at a little example here. So, so the name of the calculation comes from the symbol. It is not a multiplication, it is a cross product. So here you're given the magnitudes of two vectors and the angle between them is 55 degrees. Even though it's not mentioned, we're going to assume it's tail to tail because you are asked to find the cross product. So in the cross product notation, now what you have to realize is this cross product notation requires you to find an answer that is a vector. So this part of the formula will give you the scalar, the magnitude times the sine ratio. You need this little n notation there to have it represent a vector quantity. Okay, so we're given the two magnitudes, we're given the angle between them, there's your result. You don't know what n is in terms of direction or anything, and it doesn't really matter. Okay, so don't be too concerned about that. So very similarly in this example as well, now you notice this is B cross A. So you might be wondering, well, if this one's n, why is this one negative n? Well, as I mentioned before with the right-hand rule, A cross B will point one direction. That's perpendicular to A and B. B cross A points in the opposite direction, hence the negative normal. Okay, so that's why it's important to note what's going on there. Sometimes textbook solutions and whatnot will talk about going into the page and out of the page, and again, it is kind of a relative thing. But you can kind of think of having the positive normal vector as being out of the page and negative as being into the page for consistency purposes. So you can see I've got a little diagram here. So if A and B are on a tabletop, let's say, or a piece of paper, then the normal vector, as you can see the little 90-degree angles here, n would be coming out of the page and negative n would be going into the page. Now again, that may seem a little weird because it's on the opposite side of the page, but that's the language that's typically used, and it's not my language. Okay, so the way I would see it is coming above the tabletop or above the surface or below the surface from this vantage point anyways. Okay, so sometimes the language can get a little confusing. Okay, so we've looked at with dot product what type of results you can get and type of laws. That's all this is summarizing. It's just summarizing the different algebraic laws that are possible with cross product. So you can examine these on your own. They're pretty straightforward. So that A cross B is the opposite of B cross A in terms of, because it's a vector. So the vectors are the same but opposite direction. When you cross A with the sum of two other vectors, it's equivalent to crossing A with the two vectors and then adding the result. So again, these are all vector results, okay? And then the scalar multiple one is also there for you to view. There is something called a triple scalar product where you involve the dot product, okay? So here what's important is that you're taking a cross product, which is a vector, and dotting it with another vector to get a scalar quantity. And here, what's important is the brackets really define where you're going to get that cross product vector first. So are you going to cross u and v and then take that answer and cross it with w, or are you going to cross v and w and then get the result and cross it with u? That does matter. So that's why this is indicated here, that brackets are not really necessary with this notation because you need the two vectors to take the dot product, whereas the brackets are crucial in that type of notation. So this example is just clearly one of those similar ones we talked about before to say what kind of result are you going to get. So here you have a cross product which produces a vector. When you add another vector, you get a vector. K is a scalar here, multiplied by a vector produces a vector. Scalar, when you get a dot product, adding a vector. That doesn't make sense. You cannot add a scalar and a vector. Doesn't make any sense whatsoever. Okay, so looking at the unit vectors, I, j, and k, so some of the results there. Now again, this little diagram can help. So when you cross I with j, for example, you get k. K follows the z-axis. So you can use the right-hand rule and put you're curling your fingers, you put your hand resting on y, and your fingers are here curling towards the J. Your thumb is going to be pointing in an upward direction with your right hand rule. Okay, so that follows that one right there. We talked about vectors that are collinear. So if I and I are exactly the same vector, they have to be collinear, so your results are always going to be 0. Why are these opposite? Well, if I cross J produces a K vector, then J cross I, again, your right-hand rule, you'd be having your palm rest here, fingers curling this way, so your right-hand thumb would be pointing in a downward direction, so it's going to be in the opposite of K. And similarly for the rest of them. Now, the cross product in Cartesian form is a real challenge algebraically. I've listed it here. It's going to be in the textbook and the Google Drive if you are curious to see how this works. This is the algebra behind it. I'm going to show you a much quicker technique. It's a proof. So magically you wind up getting this cross product formula. Some students do like this formula. Okay. So if you're given two vectors with component form, this is the version of the formula that you can use to determine the vector result of the cross product, because you don't know the angle between them and you maybe can't produce the magnitude in some way. So if in component form, if you don't have the angle between the vectors, especially in 3 dimensions, this is the resulting vector you're going to come up with. So just to show you how this works, so if you're given two vectors using a unit vector form, you just have to find the cross product between them. So identifying them in component form is going to help, because that's going to allow you to substitute into this formula, which I've done here for you. Okay, so you have to be extremely cautious as to where all the numbers go. So what you're going to treat as the u and the v as well. So because the letters change too. So the formula is u and v, but here we have a and b. So a is taking the place of u, and b is taking the place of v. So you have to be very, very cautious when you're using this technique to come up with the proper results. So there you can see there were one result using unit vector form and in component form. But this is a massive challenge for most students, is to be able to figure out how this works and what's going on from there. Okay, so to show you a much simpler technique, here's the simpler technique. So you, now, when this set of instructions says write the coefficients of the first vector, that is referring to the notation. So we had a cross b, so a would be the first vector. So you write it twice. So you notice the components here, 6, -1, and 3. You're going to write them in a row, or in a straight line, twice. So you got the I, J, and K kind of listed there as references. Leave a little bit of space, then you're going to write the coefficients of the second vector twice underneath the first vector. So the second vector is B because, again, it's A. We're looking at A crossing with B. So A is the first, B is the second. So you do this little setup. Now the arrows are going to help you get all the results that you need. So if you're wondering why there's a multiplication here, you notice there's a product. You're multiplying components and subtracting them. That's what we're going to take a look at here. But the first thing you need to do is eliminate some of these values because you don't want them. So you want to eliminate the far values here and here. You're not going to use them at all in this little setup. Okay. So here's how this works then. So to get A cross B, you might be wondering where these numbers are coming from. Well, let's follow. So you've got a -1, start at the top, multiply by the 4, you get a -4. And then you subtract the product there, 5 times 3, which is 15, which matches that calculation there. So you're multiplying two values together, and then you're subtracting the product of another set of two values. Okay? Then you continue that for the J component. So 3 times -2 gives you the -6. 4 times 6 gives you the 24, and then you subtract them. And then repeat. 6 times 5 is the 30. 2 times -1 is the, sorry, -2 times -1 is +2, and then you subtract +2. And then you get your result, and lo and behold, it is exactly the same as using the formula. So you get exactly the same result, totally different technique though. My opinion, a lot easier for most students to tackle this technique, so practice this one, okay? Unless you like the formula, you can use that if you like. Okay, so how can you check this result? Well, so what this is basically saying is that this vector that you've obtained, vector v, should be perpendicular to both vector A and B. So to prove that, you can find the dot product between A and vector v as well as B and vector v, and the result should be 0 because it needs to be, vector v needs to be perpendicular to both A and B. And if it's perpendicular, the dot product between those two vectors should be 0. And that's true. So everything kind of worked out nicely there, so that's an easy way of checking. Now, interestingly enough, another vector that could have been obtained instead of the one that we found is a vector pointing in the opposite direction. It'll still be perpendicular to A and B, but it'll be opposite. So -v is also a possibility for an answer. Okay, so that is something to keep in mind when you're dealing with cross product, is there can be more than one answer. Okay, so the basic summary, your cross product formula, if you know the angle between the two vectors and the vectors are tail to tail, that's the simplest version of the formula to use. Don't forget the vector notation when you're calculating a vector. If you simply need the magnitude of the vector, then you don't need to include the little n unit vector. And why would you need that? Well, there's a little application of this cross product, and it's right in here. Okay, so the area of the parallelogram is the cross product between U and V in this particular diagram. Okay, so that magnitude anyways. Okay, so just to take a look at that. So the area of the parallelogram would be magnitude of A times the magnitude of B sine of theta. How does that come about? Well, if you remember, the area of formula for a parallelogram is base times height. Well, the base would be the U, so the magnitude of U, but we need this height. So to get that height, we use a sine ratio in this right angle triangle because it's the opposite in the hypotenuse. So the magnitude of V times the sine of theta gives us the height. Hence, there we go. So that is an application of the cross product. Okay. There are other applications that you can take a look at in the textbook, but this is the main one that you only need to be concerned about as far as the remaining part of this course.